long to compensate for yesterday, but it's also gonna be, I think, a bit wild. So, recording? Okay. So let me start. Before I start, it will be about no time, okay? No, having a picture of cosmology with no time. By the way, I hope you know where this quote is from. If you don't, do you know where this quote is from? Hmm? Hmm? Next. L. Oh, good. U. R. Huh? Yes. Pink Floyd. Okay, it's a song called Time from Pink Floyd. Okay, good. Okay, I'll hold you guilty for this. So listen to Time tonight after your steak. Don't do physics. So things I did not mention in the lectures, but I feel that for the record I should mention. So let me just state them instead of writing on the board. So first are the consequences of unitarity. Okay, the consequences of unitarity. So the optical theorem, there are cutting rules for cosmological correlators. There are non-perturbative constraints like Charlin-Lemon representation, partial wave decomposition, positivity of partial wave decomposition, unitarity and causality more generally. We did not discuss that. So that's a very interesting topic. The other is the direct connection. I mentioned briefly that there's some analytic continuation of the metric, but there's at the level of the correlators, there's a direct analytic continuation that between ADS and DS correlators, which is very useful for computations. You can connect these cosmological correlators to questions in anti-de Sitter space and then strongly coupled theories through holography. There, you can do things in position space, in embedding space. You can do direct integration also using something called Mellin-Barnes integration. So that's also an interesting set of techniques that I did not touch upon. The other thing I did not touch upon is stochastic inflation. Which is the scenario in which the quantum, remember that the massless field has very strong particle production. And if it self-interacts, this can become very strong. And then the three-level approximation that we've been using is not good. So if the inflaton, if this scalar field only couples in a shift symmetric way to other fields, then all the analysis we've done in the lectures is it's valid. But if you have a massless scalar field in de Sitter space, say with lambda phi to the 4 theory, so the theory gets strongly coupled at long distances. The logic is very simple. If you remember, lambda phi to the 4 theory is strongly coupled in dimension lower than 4, right? Very famous result. Here, the Sitter space is just stretching everything. So at short distances, we're in 4 dimensions. The theory is weakly coupled. But then as the field is getting stretched and these fluctuations are not dying off, effectively it becomes a lambda phi to the 4 in lower dimensions. In the super stretched limit, it becomes quantum mechanics of lambda phi to the fourth. So super strongly coupled. So these types of diagrams we've been drawing are not applicable. But there is a beautiful formalism to deal with this called stochastic inflation. Okay, so I did not touch on this. Also, I mean, I said that we don't know how to do loops, but people have thought about loops, including myself, but many other people have. Some people have worked very hard on loop corrections and some models of de Sitter space and inflation. I would say that things are not systematically understood, but there are semi-quantitative and lots of qualitative things that we know about loops that I did not discuss. The other thing I did not discuss, which is you saw, I guess, quite a bit from Andrea's lectures, is the issue of soft theorems. There are soft theorems in cosmology. And in particular, I did not really say much about gravitational non-Gaussianities in general. I mostly talk about a scalar field, gravitational primordial non-Gaussianities. The other thing I remember, some people mentioned they were interested in the double copy. There are like twistor methods that I became very excited about because they have something to say for gluons and gravitons in de Sitter, in anti-de Sitter also. So this I think is also really cool. Then another thing is this story of positive geometry, which is fantastic idea that there are some geometrical objects that seem to have nothing to do with space-time, from which you can get cosmological correlators. This is a beautiful subject. Something more phenomenological but also interesting is the issue of parity violation. I did not really mention anything about parity, but there are many. Parity violation turns out to be fairly constraining thing in cosmology. So not everything, but some of these topics are mentioned. If you're interested in any of them, I did not give any references for the lectures, I guess, but I can ask our organizer friends to add. I'll send them a couple of references, but there is some snow mass review on cosmological bootstrap. It's not really up to date because the subject is evolving fast, but he mentions some of these things. Okay. Our last item for these lectures is this. So this, so we were I mean, the motivation of the lectures, the theme of the lectures has really been about computing these cosmological correlators, understanding their symmetries, how to bootstrap them from these boundary kinematics. And the working horse is differential equations. So when the dust settles, you know symmetries, you know singularities, but then you find a system of differential equations that then you solve, and you can use the differential equations to find your correlators. It's neat because it's naturally sort of holographic. It really only depends on kinematic data at the time slice at the end of inflation. And a natural question, well, the two questions are they general phenomena? And the second question, is this just a calculational crutch? Or something deeper? Well, I wouldn't be giving this lecture if it was a calculational crutch. So I guess you know the answer of question 2. But I'll try to convince you that there is something pretty cool and interesting and still somewhat mysterious going on. So, well, what's the intuition for why? There's some intuition for why you would expect this not to be just some calculational. So there's some intuition. What we call time without time. Somehow the whole trick to get differential equations is this trade, this trade-off between large distances in the sky and large distances in the sky correspond to earlier time physics during inflation, and short distances correspond to later times. And this is certainly fantastic in inflation because you get like almost scaling variance. But more generally, it's also true, as long as the scale factor is not like crunching and expanding, as long as the universe has a fairly monotonic history, it seems reasonable that there is if you track a given wavelength, it's getting stretched. And then there is a specific scale, some sort of horizon scale, in which particle production becomes important. And it's this scale that is imprinted, okay? So this intuition, we're gonna try to take it to the bitter end, and I'll show you how far we can go. So let me try to describe a toy model that we're gonna learn to love for today's lecture. Toy model is a single scalar field conformally coupled. So that means that the mass is tuned to the geometry. Okay? So you tune the mass. So I'm cheating a little bit because I'm not making it completely generic with polynomial self-interactions. Oops. Interactions. But in arbitrary FRW cosmology. Okay? So it's convenient to write like this, but you couldn't imagine any power. This doesn't look like much, but it's fairly general. So just, I mean, the motivation was inflation because epsilon equals 0 is de Sitter space, so you could imagine making epsilons, and we called epsilon because of slow roll. But it turns out you can do it at any value of epsilon. You can play this story for him. So it's surprising how much you can do in terms of cosmology. So Epsilon equals 0 is like de Sitter. Epsilon equals -1 just give us back flat space, meaning there is no interesting time evolution. Epsilon equals -2 is a radiation dominated universe. So if you fill the universe with radiation, the scale factor in conformal time is given by this formula with -2. -3 is matter domination, and so on. Okay. So this is the toy model. I'm gonna make it even simpler. Maybe I keep Pink Floyd here. Let me write the Lagrangian is minus. Okay, so this is the action. I'm just gonna take phi cube theory, whatever, over 3. I'm not gonna keep track of this stuff. So the reason why we tune the mass is because then the classical mode functions for the, if you wish, for the bulk to boundary propagator or what you would choose to quantize, they are essentially plane waves. Okay, so the ik eta. And the only appearance of the cosmology in the mode functions is through this redshifting factor. Okay, so that's why if you try to solve the massive wave equation in FRW spacetime, there's no closed form solution. Even the massless wave equation in FRW is a Hankel function. Okay, so if you tune the mass, at least you get something tractable at the free level to start. But it's not that we cheated so much that epsilon drops out, because the interactions they care about the geometry. Okay, so it's not that the answer is epsilon independent. So let's get our feet wet with this theory. Are there any questions? Clear? So the goal is we want to understand 3-level correlators in this theory. Okay? So let's start. Simplest thing is just, well, the simplest thing is a 2-point function, but that is too simple. So the 3-point function, you just integrate. So let's see. 1, 2, 3. Okay. So you get eta to the -1 plus epsilon because of the root g, and there are 3 mode functions. Okay. So there's 1 over eta to the 4, and then you have eta cubed from the 3 mode functions. So you get eta to the -1 plus epsilon. So of course, this, it doesn't take a genius to do these integrals, just there's only one scale, so it's a power law. But let me be pedantic, and let's use a Schwinger's trick. I'm gonna write eta to the minus alpha to be proportional to the integral 0 to infinity. I'm going to introduce a Schwinger parameter, e to the ix eta, x to the alpha -1. Okay? I'm going to introduce the Schwinger parameter and then do the time integral and keep the Feynman parametrization. Okay, so this becomes clear. So I just take eta to the minus 1 plus epsilon. I plug this in, and then I can do the time integral because there's just a exponential of something. So this becomes integral. I traded a trivial integral for another trivial integral, so you're probably questioning me right now, but bear with me. 1 over x plus k1, 2, 3. Okay? So that's what we'll get. This is nice. Well, okay, we know what the answer is, right? What is the answer? What is the answer? Dimensional analysis, people. There's only one scale. What is the... There's only one scale. There's only one possibility for the answer. And it's not 0. So what is it? Okay, so that's the only thing that it can be. But more important is that this integral here, you can think of it as integral. Notice that in flat space, remember we did this computation a couple lectures ago. In flat space, it's just 1 over the total energy, right? 1 over k1, 2, 3. This is the flat space answer. Psi flat. But integrated against this measure next to the epsilon, psi flat, where you take the total energy, k1, 2, 3, and shift. Okay. So it turns out that this works beyond 3 points. So that's why I subjected you to this little exercise. So it's of course overkill, but it doesn't take a lot of work to convince yourself that and we're going to use this. The wave function in FLRW is given by psi flat, where you shift the energies. Okay, so I'm going to introduce some notation here, big X plus little x, where here big X are energies external that enter a vertex. Okay, so this is a little bit telegraphic. Let's do this the second example, which is already non-trivial, which is the 4-point function. So that's the first example. The 3-point function is too trivial, but let's do the S channel 1, 2, 3, 4. Now there's only one field. There's no story of extra fields and so on. Remember we studied this in flat space, right? The answer in flat space was 1 over k1, 2s, k3, 4s, k1, 2, 3, 4, right? The total energy, partial energies. So now I'm going to introduce a bit of notation. K1 plus K2, because it's associated to what's happening here, I'm going to call external energy 1. And this guy here, K3 plus K4, I'm going to call external energy 2. Okay, so X1 is K1 plus K2, X2 It's K3 plus K4. And what I was calling Ks is just because it's wired in my brain like this and it's on the paper like this. So sorry to change notation from one letter to another letter. But so the things we were calling U and V were y over x1 and y over x2. Okay, so yet another source of confusion. Y over x1 is U, y over x2 is V. Okay? So this is just some notation box. So in this notation, this becomes 1 over x1 plus y, x2 plus y, x1 plus x2. So what I'm supposed to do, so that's the flat space wave function. What I am supposed to do is so the FRW wave function is going to be integral. So now there are two x's, two external energies. There are two times to integrate over. Okay? That's the way to think about it. There are two vertices, two times to integrate over. So there will be two Schwinger parameters, d little x1, d little x2, 1 over. Then you shift the big x's by little x, x1 plus big x1 plus y. And where does the cosmology come in? Through the measure. Okay? So now we reduced our problem on the cosmological correlator in this toy model for an integral of this type. Remember that I told you that all trees can be built out of perimeters of polygons, right? To take the polygon kinematic space, you multiply all perimeters. So you're going to get a wave function in flat space that is rational in this model. And then I'm telling you that if you want to do cosmology, you take this rational wave function, you shift the arguments, and you integrate against this measure. So what does this object remind you of? In physics in general. Does it ring a bell? You have a bunch of rational functions and you integrate against some measure to the power epsilon. What does that remind you of? Loops. Right? That's what loops in flat space look like. Propagators are rational. You just concatenate a bunch of propagators and you integrate in a GMRAG in 4 plus epsilon dimensions. So here, the GMRAG parameter is the cosmology. By the way, dimensional regularization changes the infrared of the theory, right? That's a famous thing with GMRAG. It's not just softening the UV, it also changes the IR. Here, the cosmology is the change in the IR. Okay, at long distances, space-time changes. So this we're cooking because people that care about loops have thought about this problem for decades. And they have beautiful artillery to deal with this problem. And something that we can apply QCD machinery to obtain differential equations. So in amplitudes, people also are interested in differential equations, okay? So here's the trick. Well, there are many tricks, but let's introduce them one by one. The first trick is trade search for a differential equation for psi traded for system of first order differential equations for a vector. So this is familiar. It's like going from the Lagrangian to the Hamiltonian. Instead of having a second order equation, you have a system of first order equations in phase space, okay? It's the same type of trick. So, I mean, the basic idea is you build a vector, something like the original wave function, and then maybe its derivatives, second derivative, and so on. And then you find the system of first order differential equations for I. Okay? That's the first. Okay, it's a pretty simple idea. Now the second thing is, the second thing that makes this model very tractable and beautiful is that the integrand is singular only on hyperplanes. Well, here it's in this case lines, okay? But as you add more points, there will be hyperplanes. So let's draw this. This figure will be etched in on your mind if I did my job in this lecture. So we have little x1, little x2. And let me try to color code this. Call this L1. Call this L2. Call this L3. So L1 is a particular value of little x1, something like this. L2 here. And finally, L3 here. Moreover, there are cuts, right? That run through the origin. Okay. So it is singular in the sense of there being cuts. Okay. So notice that we're integrating here, so we don't see the singularities in the physical sheet. But the claim of mathematicians, now I'll just start invoking mathematician black magic, and I have no idea why things are true, but they are. So, therefore, the family of all integrals with same singularities, same singular structure span a vector space of the first. Okay, this is a triviality. You just build all the possible integrals that are singular only in these regions. But then come the two spectacular things. First, of finite dimension, equal to the number of bounded regions in the integration domain. So these are the two fantastic statements. So the first statement is, okay, we don't know how to solve this integral. So what do we do? What do the mathematicians tell us to do? Say, you don't know how to do this integral? Very easy. Now you consider all possible integrals with the singularity structure. So let's trade one problem that we don't know how to solve for infinitely many that we don't know how to solve. So you consider the general family Fn1 and 5 integral. The measure doesn't change. But now you consider x1 to the n1, x2 to the n2. Let me call this L1 to the N3, L2 to the N4, L3 to the N5, and then you're free to put coefficients that depend on the kinematics. Okay? Upstairs. So let's trade one problem that we don't know how to solve for infinitely many that we don't know how to solve. For every integer, n1, n2, n3, n4, n5, we have a different integral. So why does this form a finite dimensional vector space? For two reasons. One is partial fractions. So it's not that every new member is independent, right? Because I can write, so let's do like a simple example. 1 over x1 plus x1 plus y minus 1 over x1 equals minus x1 plus y divided by x1. So if you stick this inside of these, so you get that f n1, n2, n3 plus 1, n4, n5 minus f n1 plus 1, n2, n3, n4, n5 equals minus x1 plus y, f n1 plus 1, n2, n3 plus 1. Okay? So not all integrals are independent because of partial fractions. And the second thing is that integration by parts. It's two trivialities, okay? But they are super powerful. At some point, you build integrands that are so complicated that they magically turn into total derivatives. You integrate to 0, okay? Here, to state the theorem, it's important that we work at generic epsilon, which means drop all boundary terms. Okay? If you keep track of boundary terms, then the story is more involved. But magically, we will find that if you work, as usual in physics, if you work a generic case and then you close your eyes and you reach the end and then set epsilon to the non-generic case, things still work. Okay? Don't ask me why, but it works. So so this is the first part why it's finite dimensional, but the actual dimension is also easily calculable. Then let's look at the picture, let's calculate number of bounded regions in the integration domain. So this is unbounded, 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 unbounded. But there are 1, 2, 3, 4 bounded regions. Okay? So the claim is that if you know 4 integrals of this infinite family, you know all of them, as long as they're independent. Okay? So now we traded one integral that we didn't know how to solve for 4 integrals that we still don't know how to solve, but the strategy to land at this finite dimensional vector space tells us what to do. Tells us what to do. So now let's go back here. Let's take 4. We take 4 such integrals, and there is some a bit of baking on how you pick the bases. Okay, so it's not an exact science, it's a bit of an art. If you pick the bases wisely, and I'm going to tell you what wisely means. But for now, let's work, it doesn't matter. Pick whatever bases you want. As long as they are independent, then what is the strategy? You take the total differential, okay? Take the total differential of I, what is the total differential? You take the derivative with respect to x1 in the x1 direction, x2 in the x2 direction, y in the y direction. You take the derivative, let's say with respect to x1, okay? So what are you doing? You're just shifting around the exponents here, right? You take the derivative with respect to x1, you raise, you get the first power L1 squared plus a term with L3 squared, right? So what are you doing? You're just producing other members of the vector space. But I told you, this is a basis. So whatever you get must be expressible within the basis. Therefore, just from linear algebra, you should get something that is expressible in terms of the members of the basis. This is the differential equation. We're done. Okay? We could go home and eat steak, but I will tell you many more exciting things about this. So for this system, the existence of the differential equation follows from this amazing mathematical theorem, okay? It's a lot is known about integrals of hyperplane arrangements. They have different incarnations, have different names, GKZ systems, and anyway, it was largely developed by a whole school of Japanese mathematicians like Aomoto, Kita, and so on. Yeah. Well, because of the cuts, right? It's x1, x2 to the epsilon, a generic epsilon. And then I'm going to allow myself to consider denominators with powers of x1 and x2. Okay? It doesn't need to be, but I only allow integrals that are singular at most in these 5 different regions. Okay? Any more questions? Yeah. No, it's a space. So I mean, the field in the vector space are generic coefficients in these. Let's assume that they're polynomials in these x1, x2, and y. Okay. So instead of numbers, you allow yourself for rational functions, say, of this x1, x2, and y. Any more questions? So in that sense, the problem of differential equations is solved. But we're just starting. We're just starting. Things are going to get more spectacular as we go. Okay, I'll erase this. Oops. Let's get our feet wet. Let's do epsilon equals 0, okay? Just to get a feel for what's going on. Now, let's do. This is the de Sitter wave function, okay? And I am going to do something that it will be natural in a little bit. So now there's no measure up there, and you'll see why the epsilon is important. But nonetheless, we're going to learn something. This is the non-generic case, okay? Just to see how this differential equation system comes about. I'm going to put the 2y here. So let me maybe give it a tilde. There is no y, but the y there has a purpose in life. So psi tilde is 2y psi. Okay. Now let's take a derivative. Let's try to find a differential equation. Okay. I take a derivative with respect to big x1 of psi tilde. Oh, that's easy. x1 appears shifted. So it's a total derivative. Right? The little x1 of the same thing. Now, if I worked at finite epsilon, this would not be a total derivative. I would need to integrate by parts and get something linear in epsilon, right? But now, because there's no measure, this is a total derivative, which is equal to. By the way, maybe I forgot to say, for those that are mathematically oriented, if you want to be impressed by what I just said, this is called the twisted cohomology. Okay, twisted cohomology. Why is it called twisted cohomology? There's a cohomology in the fact that there is an operator that squares to 0, which is related to integration by parts, right? That boundary terms. That if you keep hitting this with this operator squares to 0, right? The d squared is 0. So there is a cohomology related to this operator, and twisted because of the measure. Okay, so the statement really requires the measure, the fact that you can drop all boundary terms. So you can think of it as the statement that actually inside of integrals, it's there's a derivative plus some connection, some epsilon d log of something. Okay, and you study the cohomology with respect to this guy here, just because of the x1, x2 to the epsilon there. So the theorem about bounded chambers and so on is only applicable for twisted cohomology. So this, for example, would not be the case, because we'll see that the basis of integrals that you need here, they are integrals of forms of different dimensions. I'm going to see in a second. Right? So this is a two-form integral, and now when we take the total derivative, we end up with an integral of a one form. Right? So there's integral dx2. And then I get 2y divided by x1 plus y. This doesn't change. So the 2y was there to normalize residues, okay? So what's special about this? So I need to go on a tangent for a little second. So this is a very special two form. This is called the canonical form, because it's the unique form with logarithmic singularities and unit residues at the boundary of a certain region in the integration plane. For us, it's this region here. So if you try to build a two form that has singularities only at boundaries of certain region, and you normalize the residues at the corners, then this form is essentially unique up to sign, and it's called the canonical form. It's like a D-log form associated to a region. And this is doing a lot of the magic in this model, okay? The fact that, so every time you see forms that you must integrate over, then the rule of the game, at least in this model, is to look for canonical forms. So that's why I put the 2y here, to normalize the residues. Okay. So just to give you a handful of examples before we go back to this. So this is a parenthesis, okay? I'm opening a little parenthesis. Let's start with examples of canonical forms. First example, segment in 1D. So say I take the line x, and there are 2 points, minus a, minus b. And I want to write a canonical form associated to this interval here. So what do you suggest I do? It's a one form. It can only be singular at these 2 points. So What do you think the canonical form is? Everyone happy with this? The residues must be normalized. Yes. This is, and moreover, this is the, you could have said, well, you have two choices for the, should it be a plus or a minus here? Well, now you know the answer, right? But why is it a minus? Otherwise, there are three singularities. If the sign is plus, there's a third singularity. Where? This has singularity at minus a and minus b, and there is a third one. Where? Say again? Sorry, I can't hear you very well. No. No. This is the right answer, I think, because this would be x plus b minus. So the residues are units. Right? So this is the answer. So I think this is okay without the 1/2. But the question is, what's wrong with this? Complex analysis. What are you supposed to do to check for the poles of a function? What's the behavior of the function as x goes to infinity? There is a pole at infinity. So this removes the pole at infinity, okay? So that's what fixes the sign. So that's why the form is unique. Then the only thing you have a choice of is the coefficient up front. But if you normalize the residues, then only the overall sign is ambiguous. Okay? Now, second example, in 1D, that's it. Second example is a triangle. So let's take a triangle, x1, x2, L1, L2, L3, and L1. Let me write it like this, okay? C1.x, L1, 2, 3 is, sorry, L1, 2, 3 is C1, 2, 3.x, and x is little x1, little x2, 1. Okay, just something that knows about the coefficients. Then, what do you think the canonical form would be? Maybe let me not make it so generic. Let me make it a little bit, just to not to, I mean, this is not complicated, at least for these simple shapes. Let's take this triangle. Okay, so there's a1 x1 plus a2 x2 plus a3. Okay. So what's the canonical form? Yes. And, oh, it's a 2 form. Yes. That's that's more or less it. Let's check the residue is normalized. So if we go to the line x1 equals 0, if we localize, if we take the residue, then we should reproduce the canonical form for the segment here. Okay, so let's do that. Let's take a residue. So I get, for example, dx1 over x1 wedge. Then I get dx2 divided by x2, and then I set x1 to 0, a2 x2 plus a3, which we just saw that this doesn't have the right residue. Okay, so the residue is really the determinant of the coefficients. So it would I'm just telling you the answer: 0, 1, 0, a1, a2, a3. You just make the determinant of these coefficients, which is a3, 0, 0, 0, a3. Okay. So that's it. So now if we put a3 here, then hopefully this has the right. And then you can go and check. You can go and set x2 to 0, or you can set the line to 0, and you will see that you get unit residue. I need to do one more example so you don't think I'm duping you with a triviality. So it gets interesting. Third example, what about the quadrilateral? Sorry. Sorry. No. Here in our case they are, but they don't. Okay. So now I'm on the x1, x2 plane, and now I give you four lines. Okay. C1, 2, 3, 4 dot x. Okay. Where again x is x1, x2, 1. So go canonical form dx1, dx2 divided by. So here is, let's say, line 1, line 2, line 3, line 4. So what do you suggest? L 1, 2, 3, 4. What is the canonical form? Well, it has to be singular in the 4 lines, so hopefully you have, part of the answer. So what do you suggest? L1, L2, L3. If it was just this, I would be like, what is this guy wasting my time? So what's wrong with this? This is not the full answer. What's the problem with this answer? The residue. So if I set, for example, L1 to 0, then there will be residues when L2 goes to 0. Great. So when I set L1 to 0, I'm supposed to localize onto this segment. But then there will be residue when L2 goes to 0. Great. When L4 goes to 0, great. But when L3 goes to 0, this residue should not be there. So how do I get rid of it? So where's the residue coming from? Right? I set the whole line to 0. So there's this that I don't like. Now let's set, for example, L4 to 0. I set L4 to 0. Then there will be residue on L1. Great. L3. Great. But L2, bad. And now I see that I messed up once again. Okay, let me bend the line a little bit. So there's another bad point here. So bad point 1, bad point 2, what am I supposed to do? to remove these residues? Multiply by what? Multiply is good by what? There's a line that connects these 2 points, and you don't want any residue there. So there's a numerator, okay? So last one, I can't resist, and then we go back. So what if it's what? What if it's a square? Then there's no numerator, right? Well, now we are experts, right? We know one example, so we know what has. So say we wanted to find the canonical form of this pentagon. So there are 5 bad points. So canonical form would be dx1, dx2 divided by L1, L2, L3, L4, L5. What do you suggest we do? For what do you know about plane geometry and 5 points on the plane? High school, remember, long time ago. What's special about 5 points on the plane? High school, huh? Yeah, wow. Not yes, but generic 5 points on the plane. Conic section. There's a unique conic section that passes through any given 5 points on the plane. That's more or less the definition in the analytic geometry. So, well, does it mean that we need to become like a crazy geometers to find canonical forms? And the answer, thankfully, is no. Because canonical forms also have this amazing property that you can find them by triangulation. Okay? So if you didn't know anything about this stuff, what you can do is you can take the canonical form of this triangle, the canonical form of this other triangle, add them up, and remember the residues are 1 or minus 1. So you add them up with the right relative sign so that the residue on the gluing is 0. Okay, so when you add the canonical forms associated to, so you would have what we would call spurious singularity. So this guy introduces a spurious singularity on the diagonal, you cancel with the canonical form of this other guy, and you get on the nose this answer. Okay, so if you wish, it's another way of discovering these crazy curves that pass through a collection of points. So here you would take the canonical form of this triangle, this triangle, this triangle, add them all up, and then you're going to produce naturally a complicated numerator that, lo and behold, is the conic section that passes through all of these points. Okay? So canonical forms are very special objects because they have these logarithmic singularities. So I'll just finish the sitter example, and then we can take a little break to continue. So let's go back to the sitter example. So why do we put the 2y in the numerator? 2y is what sets that to be the canonical form of the triangle. Let's see, remember I told you it's the determinant of the coefficients of the line. So the line is like 1, 0, x1 plus y. The other line is 0, 1, x2 plus y. And the other is 1, 1, x1 plus x2. And the determinant is x1 plus x2, 0, 0, minus x1 minus y, minus x2 minus y, minus 0, which is minus 2y. Okay? So that's it. So, I mean, if you want the really unit residue, okay, this minus doesn't matter, but that's where the 2y is coming from. So now that we learned that the rule of the game is to look for canonical forms, we see that the first derivative gives us an integral of a one form. So let's try to find canonical form associated to a one form. So there's this guy here, and now we must add the numerator so that this has unit residue. So the numerator is what? Numerator is x1 minus y. Okay? So we just add and subtract. Notice that this looks a bit spurious, this x1 minus y. But it's useful. So now we get this equals 2y divided by x1 plus y, x1 minus y, integral of the canonical form associated to the segment minus x2 minus y minus x1 minus x2. Okay? This thing finally is 1 over x1 plus y minus 1 over x1 minus y. Okay? So everything has unit residue. All the poles have unit residue. Okay. 1 over, 1 over. And this is again integral of a canonical form. So it seems that we're making progress. We're not destroying this nice structure of canonical form. And you see, we took a derivative and we produced some singularities. What does this remind you of? Remember, it was singular as u goes to 1 and minus 1. In our notation is x1 plus y 0 and x1 minus y 0. This is u equals this is u equals minus 1, u equals plus 1. Okay? So we're seeing the singularities of the differential equation, but we're building them step by step. Instead of landing on a high order differential equation, we're building it step by step. So now we know what to do. Well, we declared that this is an integral of a canonical form. Now we are in love with canonical forms. Every time we see a new one, we collect it. Okay? So now we made progress. We collect a new canonical form. And we call it F. So to get the system to close, I must study the differential equation of F. Now we take dx1 of F. dx1 of F is integral, sorry, I think yes, the integral dx2, the x1 dependence is only, sorry, let me just, this is 1 over x2 plus y minus 1 over, is this true? No, it's the other way around. 1 over x1. Right? Agree? So now if I take the derivative with respect to x1, this goes away. And again, I get total derivative. Oops, there's no x. What am I talking about? I'm going crazy. So there, x1 derivative, it's the same as the little x2 derivative. So integral dx2, d little x2, 1 over. Which is our old friend, total energy. Okay? Which is a new function. It's now a zero form. let's call it z, that we now must study its differential equation. Well, this one, I can do it here, right? dx1 z is minus 1 over x1 plus x2 z. I discovered no new function, the system closed. Okay? So I found the system of differential equations, at least in x1. So dx1 of psi f z equals 0, 0, 0, 0, 0. No. Is that? No. That's too. Okay. Let's do it slowly. That gives me 1 over x1 plus y minus 1 over x1 minus y, 0 psi f z. Then the derivative of f gives me, okay, sorry, I made a mistake. Apologize. I committed the sin of not following my own advice. So I'm supposed to identify things with unit residue. So z here is 1, okay? So this is the denominator times 1. Okay, so z is 1. So dx1 of z is 0. So it's 1 over x1 plus x2 times 1, which is z. Okay. And this is z. Okay, so now we're happy. So this is the system. If you were to take the the derivative with respect to x2, then you produce one more function just from symmetry, okay? You produce one extra function in the first step. So if you were to do the whole thing, then you would get psi f tilde z, and looks something like this. 0, 1 over x1 plus y minus 1 over x1 minus y. Then on f tilde is if you were to take the x2 derivative. Z again is just a constant. Psi f tilde z. Then f, you just get z. F tilde, you just get z, and z, you get 0. This is the system of differential equations, okay? The system of differential equations which the diagonal is 0. First of all, everything is beautiful about it, okay? It's upper triangular. If you think of this as some Hamiltonian with which you're going to do, so this looks like a Schrodinger equation, right? D something equals H something. So you would solve with a Dyson series. But the Hamiltonian is triangular. It's upper triangular. The diagonal is 0. It actually, if you take enough powers, the Dyson series stops. Okay? The answer is a polylog. It's a dialog. So you just need to expand 2 terms. Everything is very neat about it. And it has all the singularities that we learned about. It has the singularity in the partial energies, the singularity in the total energy, and it has the singularities that we must forbid. Okay? They're all there. They're all there. So this is the system of the differential equations. So let's take a break, and then when we are back, I'm going to show you how the story gets modified. I'm going to show you in the picture of the integration plane what happened pictorially, and then I'll show you what happens when we keep epsilon finite. And then we're going to do a more complicated example. and then something fun will happen. So let's take a 15 minute break maybe. So we're back 4:20. Is that okay? So then I continue without slides, and then if it's possible, yes. Then because you'll get. So what's going on? Let's. Every time we take derivatives, we're kind of localizing in certain regions. So if you look at the integration plane, x1, x2, and now I shouldn't have erased the figure, but I think it was like this, and I don't know. Here, blue. So what's going on? So if I take, so I start with the canonical form here, and the Sitter space, the lines at the origin don't play any role because I don't have the factor of x1, x2 to the epsilon. But when I take the x1 derivative, I'm localizing. I'm essentially sort of localizing to x1 equals 0. So then I end up with a segment in x2 that is singular in x2 equals minus x2 plus y, and x2 equals minus x1 minus x2. So I localize to, so when I take the x1 derivative, I sort of jump to this segment here, right? So I jump to this segment. And then when I, well, I don't know how to depict it. Then the last one, I just jump to something that is independent of x1 and x2. Okay? That's more or less what's going on. So then, and likewise, if I do it in x2, so these are the x1. So I'm moving around in in the space of forms, but here it's special because I started with an integral of a 2 form, I land on an integral of a 1 form, and finally on an integral of a 0 form. Well, here if I take instead of derivative with respect to x2, then I start something like this. This is related to f, this is related to z, and this will be f tilde, okay, and then bx2. And the picture is consistent. Like if I take derivatives in different order, I'm supposed to land in the same place and so on. So that's to say, for example, if I take a dx2 derivative, I should always also land. And then, of course, this gets taken if I take the x1 or x2 derivative. I get 0, right? So I don't discover anything new. And then it doesn't depend on the order that I take derivatives, okay? So if I take dx2, dx1, or dx1, dx2, I land in the same place. Okay? So this is a constraint actually on the matrix. So if I write di equals ai, the derivative, this squares to 0, which implies that 0 equals the ai plus a di, but a di is ai, which is the a plus a wedge a I. So this must be 0, okay? Here it just so happens that, and we'll see why in a second, These are separately 0. You see, because I had made a mistake, by the way, before the end of the lecture. I wrote the denominators, but it's really, you should really think of it like this, d log, because if I take the x1 derivative, then, for example, these guys are 0 because there's no x1 dependence. If I take the y derivative of pseudo, I would generate all 4 terms appearing here. So that's the right way to. And it all descends from this canonical form story because they're d-log forms. But somehow you integrate d-log forms and you end up with coefficients that are d-log-like. And they have the ladders, the singularities of the differential equation are exactly where you expect them to be. So what happens the moment that I turn back on epsilon? So I go back to FRW. By the way, if you are good enough in Mathematica and packages and stuff like that, this integral is actually doable. If you straight up plug it in Mathematica, you're not going to do it. But with enough effort, you get something that looks like this. C1. I'm not going to write everything, but it looks something like this. C1 x1 plus y to the epsilon. There's some hypergeometric function. Hypergeometric function depends on 3 numbers. The numbers are related to epsilon. And plus C4. Same thing with x1 replaced with x2. Okay, so that's what the answer looks like. So that's just to say that there is a closed form answer, but we're going to find the system of differential equations. So now what happens is, let's just get a feel for what's going to happen. So when I take the first derivative, oops. Same story. Now there's going to be a d little x1 of the integrand. But now there's a difference. When you integrate by parts, you don't get, it's not an integral of a total derivative. You're going to integrate by parts. You're going to hit this. So you're going to get something. Nice thing is that it's linear in epsilon. So you're going to get minus epsilon integral. And now you're going to get 1 over x1 Oh, same story, same measure. 1 over x1 times. And this is where this twisted cohomology business comes in, because now you're going to have okay. I have to go to a Zoom link. Yeah. Yes, but how? Let's see. What's the Wi-Fi that I must join? But it doesn't work. Let's try. Typically doesn't work. I do wrong. Yeah, it doesn't work. So let me try the Firenze Wi-Fi. Zoom. Meeting. What is the? How do I join? Uh-huh. Uh-huh.
Recording in progress.
Okay. So how do I? No, I just mute. Uh, okay, so let's see. Yeah, I keep it this here for now, and then how do I? How do I minimize this? Mhm. Okay, good. Okay, but for now, we just to keep the figure there, and almost the same color coding. But so now the difference is that I get this one. So the same procedure that was sending me here gives me now again a 2 form instead of 1 form. So what's going to happen is that I end up getting a little bit of the original psi, but now I produce a new 2 form that is morally related to F, but it's really the 2 form associated to this triangle here. Okay, so that's the novelty. So I move around in the space of 2 forms. Likewise, if I take this derivative, I land here. So now, if I take the derivative of this guy with respect to x1 or x2, instead of localizing to a point, I project onto this line here, and I end up the last 2 form, the one associated to z, is this one. Okay? But then the procedure more or less goes through. So these are the definitions of f tilde, and z. So this will be visible on YouTube, or I'm just yeah. Okay. Oh, interesting. Okay, so the idea is that you're supposed to build the canonical forms that now have these bounded regions. So let's see. So f, for example, would be the canonical form in which you substitute this line L1 by the line at the origin x1. So it would be f would be integral 0 to infinity dx1 dx2 x1 x2 to the epsilon. So there was the little x1 plus x1 plus, you substitute that, because you localize, you substitute by little x1, which is related to the new denominator that appeared. And the other guys you don't touch. Now let's, because we like canonical forms, we would like to normalize the residue. So it's 1, 0, 0, this line is 0, 1, x2 plus y, and this line is 1, 1, x1 plus x2. So then here the determinant is going to be x1 minus y. Remember that we naturally generated this. So now it appears as proper normalization of the residue of this canonical form. Okay? So this is f. So now I claim that if you take dx1 of psi, you should be able to rewrite the answer, which is just 2y divided by L1, L2, L3. You should be able to rewrite this in terms of something times f plus something else times psi itself. Okay? You generate only one new function. Okay? And in order to see that, we just use the facts that the x1 minus x1 plus y is independent of integration variables. It's minus x1 minus y. So we can plug this in. Let's see. So we plug this in, and we get 1 over x1 plus x1 plus y. We just partial fractioning this essentially. Okay, so I get 1 over x1 minus y, 1 over x1 minus 1 over x1. Sorry. Yes, minus 1. Okay. So I just take this, plug it in there, and I'm gonna produce. So you see, this is gonna give me back psi, and this is gonna give me f inside of the integral. Agree? So what's the conclusion? I'm getting something, when I take the derivative, I'm getting something that is linear in epsilon. When I partial fraction this object here, I'm going to get something that gives me a new function that I'm calling f. You see, I just substituted little x1 for the line L1. And I get back the original function itself. I remove the little x1. Okay? So I can carry on, but I'm not going to torture you. This is the answer. So let me walk you through this. So these are psi, f, f tilde, and z. And do you have a stick or a pointer or anything like that? No? Ah, yes. Great. Okay. So the differential of psi, I see. This is very, okay. That's too bad. Okay, so I'm introducing some pictures to keep track of the denominators. Okay? So I took only the derivative with respect to x1 of psi, and then if you could see, then you would realize that x1 only appears. So you see, this is just a mnemonic for these 5 letters. You can have denominator 1 over x1 plus y, denominator 1 over x1 minus y, 1 over x2 plus y, 1 over x2 minus y, 1 over x1 plus x2. So here I'm just going to tell you. Here I have this. So I take kinematic space, x1, x2, and y. Okay. So where does this come from? It was K1, K2, K3, K4 in our 4-point function in the S channel. Then I look at the dual graph and I make this little dumbbell picture. So this takes energies 1 and 2 is what we were calling x1. This is x2 and y. And I put a little cross to keep track of whether it's x1 plus y or x1 minus y. So x1 plus y would be something like this, and x1 minus y would be something that encloses the cross. Okay? So this is d log x1 plus y, and this would be d log x1 minus y. And finally, if I enclose the whole thing, the log of x1 plus x2. Okay? So if I take just the x1 derivative, I'm only going to see these 3 letters. I don't see the x2 letters because they don't, x2 plus y, x2 minus y don't depend on x1. So there are only 3 letters if I take x1 derivatives. So if I take x1 derivatives, I get d log of x1 plus y times psi minus f, and d log of x1 minus y times f. Okay? Then if I did the x2, I would get the symmetric. Now I got a new function. I must study its differential. And then if I study the differential of f, I am going to get f itself with the letter x1 minus y. Okay? You see, f appeared alone with the letter x1 minus y. I get back the same letter times now f minus z. I discover a new function, z. And z is now the integral of the 2 form where you substitute both of these lines by x1 and x2. So z will be now integral dx1, dx2, x1, x2 to the epsilon divided by x1, x2. I wish good luck to who's going to edit this because I'm going back and forth between the board and the slides. But okay, coming back to the slide here. So this is z. And then, well, you can stare at it and it's obvious that z is just a power law, right? There's only one scale in the problem. You can factor it out and you get a number times the power of x1 plus x2. So this just closes. This z is proportional to itself. And notice that now you get a 2 here. And one way to think about it is that the ladder now encloses 2 of these little balls here. So that's the system. So now I want you to stare at the, I don't want you to fall asleep, but let me, yeah, sorry, 1 second. So can you see these bubbles, if everything is there, yeah? So now notice that the bubbles, every time I take a derivative, the bubbles are growing, okay? So I take one derivative of psi with respect to x1. I start wiggling around the energies x1. And then I create a new function, and the tube grew. Now I take this function f. If I keep kicking it with respect to x1, the bubble grew further, and now it encompasses the whole kinematic space. So there's nowhere else to go. If I kick this guy, I just get back itself. So we call this kinematic flow. We're moving in kinematic space, okay? But we're just trying to build this static system of differential equations for the cosmological correlators. And likewise, if I kick around x2, then things grow in this direction. Now, you can go to the next, sorry. Let's go to this example. This is the 5-point function, okay? The 5-point function depends on 5 pieces of kinematic data. X1, so this is the pentagon, K1, K2, K3, K4, K5. And this little bubble here is X1 plus K1 plus K2. This little bubble is just K3, but we call it X2. This little bubble is K4 plus K5, we call it X3. So now there's X1, X2, X3, Y12, Y23, okay? Now, remember that there was a nice way of getting the flat space wave function from perimeters, right? And we identified the integrand with this bubbling here. Okay. Let me go back to, sorry, close your eyes for a second. Let me go back to the board. Let's say that we would like to describe now the next example, which is, I promised you a story for every tree. So as usual in physics, you need 2 examples to draw a line. So the wave function here will depend on x1, x2, x3, y12, y23. Okay? It has if you want to normalize the residues and put a tilde, you need this for y12, y23, and then you get L1, L2, L3, L4. Where L1 is the total energy, x1, 2, 3. L2 is x1 plus y12. L3, the guy in the middle talks to both edges. L5 is, remember, you can enclose x1 plus x2 plus y23, right? There's x1, x2, y23, x3. So this is related to this bubble here. L6 is x2 plus x3 plus y12. Okay? So this is the answer for the flat space wave function. So now you're supposed to shift the 3 axes and integrate against, so the FRW wave function is integral dx1, dx2, dx3 xi plus little xi, and the y's you don't touch. Okay. So now you have an integral over 3D space. I can't draw the picture right now. If you can draw, I would love, I tell everyone this, if you can draw the picture, I would love to see it. I would love to see it. I've been dreaming of seeing it for years now. So there are 9 planes. There are these 3. So these guys here form a double pyramid. Okay, it's 6 planes. They form a double pyramid. I think with square base. No, it's a 6 plane. So it's just a 2 tetrahedra glued. But now you add the 3 planes at the origin. Another way of thinking about it is that you have the 3 planes at the origin, and then you have these 3 parallel planes. They form a cube. Just like there, the 4 lines form a square. And the 4 lines that form a square get slashed by the yellow line. Here I have 6. These 3 guys plus these 3 guys form a cube, and they get slashed by this one is diagonal in all of the lines, and then these 2 guys are parallel to one of the lines. So I was quizzing people now at the break. You go from a little cube to 25 bounded chambers. Okay, so you can. There's a mathematical procedure to get the number 25. But now physics is kind to us. It turns out that you only need 16 master integrals. You don't need a 25 by 25 dimensional matrix. And one way to see that is that if you took 25 generic matrices, you would produce denominators, singularities in the differential equations that have no physical interpretation. Okay? So remember that the singularities must be related to factorization, right? Either you send these guys to the past or this guy breaks, and you can just count all of them. And you can check that there will be a 16 by 16 system of differential equations that describes this wave function. After a few months of computing this, you start drawing pictures to keep track of the 16 by 16 matrix. And now I'm going to tell you to suspend belief in the laws of the universe and play a game with me. So first of all, the 16 appears naturally from just bubbling kinematic space. Okay? So this is the kinematic space, and now I tell you to build the basis of functions. I just build bubbles. The bubbles must always enclose one of the balls. The bubbles can enclose a cross, but the bubbles never overlap. And if you play this game, you will find that there are only 16 possible tubings of the graph. This is the original wave function, and more or less every time you draw a bigger tube, you apply one of these substitution rules. You take one of the planes and you substitute by one of the twisted planes. So remember, there are only 3 substitutions you can do, because every time you take a derivative, you project, right? In this example, you could substitute something for the line x1 or something for the line x2. So there are only 2 substitution rules. Here there are only 3, so that's why the picture is presented like this. So I can do a substitution in x1, in x2, in x3, and I can only do at most 3 substitutions. So that's why 1, 2, 3 substitutions. Okay? There is a little novelty here because there are 3 ways of substituting the guy in the middle. Because the guy in the middle can now have singularities with negative sign in y12 or y23 alternatively. Okay, so that's why you get, you could have asked, so why don't I get 3 on the first step? Because here the only new ladder you can generate is x1 minus y, x1 minus y12, or x3 minus y23. But for the guy in the middle, you can do x1 minus y12 plus y23, x2 minus y12 minus y23, and x2 plus y12 minus y23. That's why you get 3 extra, these guys. Okay? So there are these substitution rules, and then you keep doing it, and you see that at some point the procedure halts. So these are these tubes have nothing to do with denominators. They're just a way of producing basis functions, the 16 entries of the matrix. Now, next step, I'm not going to torture you with building a 16 by 16 matrix. I'm going to show you how to build one line. That's going to keep us entertained enough. So I would have to tell you how to sorry. I would have to tell you how to build the differential of each of the functions. So this is the original wave function, then 5 more, then I think 7, 1, 2, 3, 4, 5, 6, 7. 7 more and 3 more. By the way, there are all sorts of cute things about this that scream of geometry. 1 minus 5 minus 4 plus 7, 3 minus 3 is 0. The alternating sum of these things is 0. It persists to higher points. So anyway, then we discovered that mathematicians were studying some tubings of these types of graphs, and they get the exact same structure. So there's all sorts of crazy stuff going on here. But now I want to tell you some rules that allowed me to build the differential. So this is some integral in x1, x2, x3. I could write it to you. You could use the partial fraction, integration by parts, go to Mathematica, spend a couple of days working out how to write this in terms of integrals of other canonical forms. It turns out that for this guy, you only need to know itself and 3 other master integrals. But I'm going to tell you the answer just by drawing pictures. So, as I said, forget math, physics. They're just rules. So now the first rule is, remember this was just a function, but now I'm going to generate letters, denominators that appear in the matrix A out of the function. The first rule is we call activation. So you color one at a time the tube. So this had 3 tubes. I open up 3 branches of a tree. Okay. Now the second rule is called growth. Growth says the following: if a tube already encloses a cross, you stop, you don't grow. But if the tube encloses a cross, you're allowed to grow. So this tube here is allowed to grow. This tube here is allowed to grow. So they both grow, but tubes must never overlap. So when this tube overlaps with this guy, they merge. That's another rule. I'm just making up rules, okay? I'm allowed to. Now this guy grows, and it produces. Yeah, anyway, I'm going to tell you about this in a second. And just because I need to make up rules, the last rule is if I grew towards an x, and there's a tube that is adjacent to it, I'm allowed to also have one extra step in which I absorb it. Okay, and then the procedure holds. Here I don't continue because this absorption thing came post-growth. Okay, so this grew, there was a tube sitting right next to it, and it absorbed. It's not that I grew all the way to here and then I'm allowed to absorb this guy. Okay, that's why this procedure holds. Now you go back to the list of functions and you see I produced new tubes. This had this tubing pattern. Now I have a function. I must look at my list of functions. Let's go back. I go back. So I started, I think, from this tube here. So when I grew in this direction, I produced the function that has this bigger tube here, which is this one. Okay? Or I produce this function here, which is this one. Or finally, when I do the absorption, I get this one. Okay? So I produced, and you see this pattern of growing tubes. And I only care about the tubes at the next level. I don't go back. I only move forward, and I don't go much further than one level. And so these are the functions that we gave arcane. This doesn't mean anything, okay? It's just our lack of creativity. So Q1, this is big Q1, this is little Q1, Q tilde 3 and Q tilde 2. And in the absorption rule, we say that when we absorb, we must put a minus sign here on that function. And now we can just build the whole entry. So let's read from the tree the whole entry of the differential equation. Remember that the functions are related to tubes, but these colored tubes, they also know about denominators. So now I go and read. So this, I have only this red tube here. What is the red tube? Is 1 over big X1 plus Y12. And then I'm supposed to collect the function and its adjacent. So I get the function itself, Q1, and its adjacent, which is little q1 with a minus sign. Okay, multiplied by this letter. This letter is now, sorry, I hope it doesn't cause confusion. So the tubes do double duty. They characterize functions and they also characterize denominators. This is d log of big X1 plus Y12. Now I go to the next step of the chain. I see little q1 and it multiplies this letter. So this letter, what is it? Is d log of big X1 plus X2 plus Y23. Okay? And then there's nothing to its right, so it stops. Now I go to this guy. It's just big Q1 itself. There's nothing to its right. I just repeat Q1 and this letter. What is this letter? It's d log of X2 minus Y12 plus Y23. This guy here, finally, well, the first procedure is identical. I copy big Q1 minus Q tilde 3. It's adjacent. Then Q tilde 3 multiplies this letter. This letter is X3 minus Y23. Its adjacent is now minus Q tilde 2. So that's why the sign of the absorption rule was important. I flip a sign, and finally, minus Q tilde 2 multiplies this letter, which is X3 plus X2 minus Y12. And lo and behold, this is a line of the 16 by 16 matrix that I gave you just by drawing pictures, and no integrals were harmed. Okay? And I have no idea why it works. Okay? It just works. And you can go and now go home, have steak, and in the weekend you can draw your favorite graph, apply these rules and predict. And we have a code on the archive that you can then check. We do this for crazy graphs, okay? You can do it for, the size of the matrix is 4 to the number of propagators. So you can do it, for example, you can do for this graph is a 64 by 64 matrix. You can go, I want to predict line 45. I go draw some tubes, the tubes grow, there's absorption, I read off all the letters, you can go hit the mathematical code that is on the archive listing of this paper, and if you understood the rules, you should predict everything without touching any integrals. And this is dynamics in kinematic space. It knows about time evolution, even though you're just touching some tubes. So I'll leave you, well, there's still some time, so I will probably leave you with this because, I mean, that's a climax, I guess. One more thing that I wanted to say is you can do this for the sum of diagrams also. You can decide to color the theory and look at planar diagrams. So for example, you can decide to study theory like that. So instead of phi, I was calling var phi. So you just make it charged. And now the diagrams will have a double line type of notation. And you can consider just the planar graphs, for example. So that would be 1, 2, 3, 4 plus 1, 2, 3, 4. Okay, there'll be only S and T channel. You can consider the sums of graphs, and you say, well, I want to find the differential equation for the sum of graphs. And you said, wow, that's really dumb. I just take each graph, take its matrix A, and just concatenate them. I'm done. But here is you can do a little bit better than that. So the naive size of the matrix A is 8 because it's 4 by 4 for each graph. There are 2 such graphs, but the real value is 7, so you're not very impressed. They share one common function, which is just the total energy function, right? So that's not very impressive. But now if you crank up the number of points, so at 5 points there are 5 diagrams, okay? You can count. These are called Catalan numbers, the number of diagrams that appear at each order. So there are 5 such graphs. Naively, this is 5 times 16, and you can actually find a matrix A that is 56 by 56. And okay, it gets much better at 6 points and so on. And there are rules for tubes, but now in the full kinematic space. So instead of tubing, say, just something like this, you would go in the full kinematic space, and then, for example, you triangulate like this, or so at the first step, you take full kinematic space, and then you triangulate like this, or you triangulate like this, and you can color the left or the right, the up and the lower, and so on, and until eventually you reach the function where you just painted the entire kinematic space. Okay, so it's the same story for the tubes, but now for the full kinematic space. It's related to triangulations of the polygon of kinematics. So there's also some story here. The thing I forgot to tell you is that there's only one free parameter in this whole story. There's only one free parameter. So this is completely fixed by these rules, but the number up front is what's left as a free parameter. And for us, it's epsilon, it's the cosmology. Okay, so you can dial this number up and down, and you change the cosmology, and then you see that it's coming from twisted cohomology. A natural question is what happens when epsilon equals 0, because naively it looks like the matrix A just vanishes, but that's too fast. You need to rescale. So for example, the diagonal entries will all disappear, because no matter what rescaling of BQ1 you do, you cannot get rid of the fact that this is epsilon times Q1. But then you can, for example, rescale the little q's and send epsilon to 0. You just delete the diagonal, and the off-diagonal terms survive. So that's how you're going to land back on the system that I worked out at the end of the first lecture. Okay. So I'm going to get out of Zoom because this echo is driving me crazy. Okay. Very good. So, well, how do I conclude? I mean, this was a surprise, okay? It's not like, yeah, this model for sure holds some amazing rules that we were just interested in this model. We poked around, the equations got complicated, we started drawing pictures, and the pictures have life. Okay, so we're just following our nose. We're interested in this model, and we're trying to see how far we can push. Now the rules are interesting. would like to understand them. I don't even understand operationally how it's manipulating the integrals and generating these various rules. The other thing is that you could have said, well, you're just doing some dumb model of a scalar in FRW. Who cares? I'm interested about the Sitter space, masses, spins, or whatever. And this model is not so dumb. Like you can start modifying it, adding bells and whistles to it to mimic something more realistic. So I'll just give you one example. Which keeps us in the same realm of integrals of canonical forms. So if you take the flat space, I was telling you that if you take the flat space wave function and you shift x to x plus little x and keep y intact and you integrate x to the epsilon, you get FRW, right? Now there's something else you can do. You can take psi flat, same story, x to the epsilon. But now you take y and you shift y and you integrate against this kernel here. Now I claim that this is the FRW wave function with unparticle of dimension delta. Meaning, this is the diagram where you take this to be a CFT operator, O, with dimension delta, O delta. Okay, instead of a two-point function of conformally coupled scalar. This is very nice because it keeps us, the integrand remains integral of a bunch of hyperplanes. I just introduced an extra integration variable. So now the number of integrals is not related to the number of vertices in time. There's an extra integration variable, but it's still, the integrand has some singularities in lines, t equals -1 and t equals +1. It turns out that if you want to do massive fields in the Sitter space, similar version, maybe a slightly more dressed version of this story goes through. You can do masses in the Sitter space, where now the delta would be related to the mass of the particle in the Sitter in Hubble units. There's a little bit more that you need to do to get there. So that's to say that, and of course we don't know if there are these flow rules that apply, but I don't see why some version of it would not exist. Okay, so to me it's very exciting because there's these rules, they come out of nowhere and they seem to describe the correlator. And the physics again is this story of seeing time evolution by just wiggling around the diagram. So the intuition is the one I was giving you in the beginning of the lecture, but now for the whole diagram. So if you take, why is it that the procedure halts? Okay. I take the wave function, I take one derivative, I explore, I wiggle these guys around, I explore a little bit of the Feynman diagram, okay? That's after doing one derivative. Now I take two derivatives, I explore the whole thing, so the procedure is over. Now that makes a prediction for how it should work here. If I take one derivative, I explore a little bit. If I take two derivatives, I get here. If I take three derivatives, I can go further, right? Something along these lines. It's morally true, but the order of the differential equation is still a little bit of a funny thing. So what is the order of the differential equation here? The order of the differential equation is, if I want to find an ODE, so now let's go back to the original wave function. What is the order of the ODE? Is there some differential operator in x1 that annihilates it? For this example, the order is 3, okay? It's a D3 x1. Why is it 3? One way to think about it is that with two derivatives, you can build the Klein-Gordon operator, like we were doing in the previous lectures, that give us the total energy. And total energy, I can just, if I get some second order operator, total energy here is 1 over x1 plus x2. I can just rewrite this as 1, and then I take one more derivative, and 0. That's my third order equation, okay? So you would have thought that for this diagram, the order of the differential equation must be 5, because with two derivatives, I collapse this propagator. With two more, I collapse this one. I get 1 over total energy. I play the same trick. I get a fifth order equation. And you would be right. One of the reasons why this question was interesting a few years ago was, wow, if we're really saying that you can wiggle the points around and find a differential equation, what are you supposed to do here? Can you just wiggle, take x2 derivatives and take enough of them that somehow you kill the whole diagram? And I welcome you to try. It's pretty damn hard. I have actually, to this day, don't know how to do it, to manipulate this with x2 derivatives to engineer the Klein-Gordon equation on the left and on the right and kill these propagators. But now we know the equation exists. Just from the matrix. From the matrix A, you can read off the differential equation. There is an ODE in x2 that kills this. There's some high order operator. I think, I don't remember, I never remember the number, but it's not 5. Here, if you come from the left, you get 2, 2 plus 1, 5. In the middle, it's something like 8 or 10, I forget. 8 or 10. Or the derivative in x2 that will kill this wave function. Okay? Why? I don't know. It's somehow, these differential equations are encoding this space-time locality in a way that still somewhat mysterious to me. Okay? So that's, and I can tell you, we tried for almost a year to play around with this and try to find a differential equation, and we failed. But with this matrix A, you can get whatever differential equation you want. By the way, to get the differential equation, just linear algebra, right? I said that there is a di equals ai. So that makes a prediction for the order of the differential equation, right? If you change bases and you put here the wave function, its first derivative, second derivative, third derivative, it's just a change of bases. So at some point you get n plus 1 vectors in an n-dimensional space. They must be linearly dependent. That's the differential equation. So there's already a surprise, because here the matrix A was 4 by 4. di plus ai is 0, but this was 4 by 4. And I'm telling you that the differential equation is of third order. That means that if I take psi, its first, second, and third derivative, they're linearly dependent, even though naively they are 4 vectors, but they're not spanning the whole space. That's an extra magic of the physics of the process. So the size of the matrix, which I told you is 4 to the number of propagators, would predict that the differential equations are of order 4 to the n. So 4-dimensional ODE, 4th order ODEs for single exchange, 16th order ODEs for double exchange, and I'm telling you it's much less. It's 5th order in x1 and x3, it's like 8th order in x2. Also getting these orders from the matrix A is still a mystery to me. So this model is surprisingly rich. It has some crazy structure behind it. And that's my take on holography for cosmology. We've been trying to look for a holographic duo of cosmology for 20 plus years. The SCFT, weak rotates, like do something around what we know in ADS. And this seems to be a structure that has some version of locality in kinematic space, and it's building you something that tells you about the dynamics of these correlations, of these primordial perturbations in an expanding space-time. It's really pushing this picture of if I wiggle this around, I'm moving the time up and down to its most extreme consequences, making it precise. So that's more or less what I had prepared. I could go into some of the topics that I said I would not cover, but I think that given that it's Friday, maybe I will stop here. I wish you very best of luck in your studies, in your research, that you find something that you're passionate about, a nice problem to work on, and well, we'll see you around. It's a small world, so.